they sleep silently, hiding within the Earth's crust. But if they awake, they can kill millions and disrupt the fabric of modern society. They are called supervolcanoes. Thousands of times more powerful than any recent eruptions, their ash and gas can cover a continent. But what makes these mega monsters even more dangerous is how little is known about them. Now, 4 scientists working independently from the Arctic to the equator are all uncovering clues that lead back to one of the biggest supervolcanic eruptions of all time.
The devastation that it caused was unimaginable.
All hell would have broken loose.
75,000 years ago, a supervolcano brought fire, famine, and death to a quarter of the globe, and may even have plunged the planet into an ice age. Can these scientists locate the fiery beast? And will it erupt again? Up next on Nova, mystery of the mega volcano.
Corporate funding for NOVA is provided by Google. Major funding for NOVA is provided by the Howard Hughes Medical Institute, serving society through biomedical research and science education, HHMI. Major funding for NOVA is also provided by the Corporation for Public Broadcasting and by PBS viewers like you. Thank you.
There are more than 1,000 active volcanoes on Earth. About 50 erupt every year. Many are well known. Vesuvius, Pinatubo, Mount St. Helens. But these fire-breathing mountains are dwarfed by a type of volcano discovered only in the last few decades. A supervolcano. Now, evidence of one of the most powerful of these super eruptions is emerging in a most unlikely place. Here, on a flat, icy tundra, less than 1,000 miles from the North Pole, the mystery begins. While on a routine mission, researchers for the Greenland Ice Sheet Project uncover the first clue. They are searching for a place to drill into the ice. This ice is an accumulation of more than 100,000 years of snowfall. As snowflakes form, they capture chemicals in the atmosphere. Over time, the snow is compressed into this ice sheet, now a mile thick. To read the chemical history, the researchers drill ice cores. The deeper they drill, the further back in time they go. Climatologist Greg Zielinski is an expert at finding secrets frozen in this ancient ice. By analyzing the composition of each annual layer in the ice core, he finds tiny chemical fluctuations that correspond to periodic shifts in temperature and climate. One day, Zielinski gets the shock of a lifetime. Something in the ice that defies all logic.
When we got back to about 75,000 years ago, we found a particular piece of ice that gave us information that was just so exciting.
What Zielinski sees is a huge leap in a particular noxious chemical, concentrated sulfuric acid.
The concentration of the sulfuric acid was on the order of 2,000 to 4,000 megatons. That's a lot. That's a lot of material to be up into the atmosphere.
In fact, it's up to 25 times more than all industrial sulfuric acid pollution produced over an entire year on Earth today. This line on the graph hints at a global event of unprecedented scale, 75,000 years ago. Billions of tons of sulfuric acid somehow found its way into the Earth's atmosphere and blanketed the planet in a poisonous yellow haze. Where did it all come from? Something extraordinary must have taken place.
The more I looked at the results, I knew we were looking at something that was just cataclysmic.
Zelinsky and his team know something significant happened to the Earth 75,000 years ago. But what? Thousands of miles away, another mysterious clue arises in an entirely different place. The deep ocean. Like Zelinsky, geologist Mike Rampino studies the history of our planet's climate. But instead of deciphering ice cores, Rampino investigates ocean cores, layers of sediment drilled from the sea bottom.
In ocean cores that we use like this one, you can often see the changes in temperature and climate, like changes in color in the core.
Rampino can trace shifts in the Earth's climate from something in the cores. The shells of tiny sea creatures called foraminifera. While forming their shells, these minute creatures absorb oxygen from the seawater. But that oxygen can be one of two forms, or isotopes, that have different mass. Lighter oxygen-16, or heavier oxygen-18, which is more abundant in colder water. By measuring the ratio of these two forms of oxygen, Rampino can calculate ocean temperatures over many thousands of years with amazing precision. Rampino analyzes ocean cores from all over the globe and finds that the oxygen ratios in the shells of foraminifera remain fairly constant. That means ocean temperatures also have remained constant for long periods of time. But one day, Rampino sees something bizarre in the oxygen ratios. A point in the Earth's history when ocean temperatures plummeted.
At the time, I thought, there's something wrong here. This isn't normal. This isn't the way climate usually works. It usually works on a much slower, more steady basis.
Rampino's seashells are telling him that ocean temperatures dropped nearly 10 degrees Fahrenheit over just a few thousand years, which in the Earth's 4.5 billion year history is the blink of an eye.
The temperature change that we saw in these deep sea core records was something like 5 or 6 degrees Celsius. That's 10 degrees or more Fahrenheit. Not over 100,000 years or even 10,000 years, but over just a few thousand years. Now, climatically, that's very surprising. That's very, very fast. That's very catastrophic.
To Rampino, the cooling seemed like an unusually sudden onset of an ice age.
It was like flipping the switch on the global climate system from hot to cold.
Then Rampino calculated the date of this steep drop in the world's ocean temperatures. It was 75,000 years ago. The same time Zelinsky's ice cores showed massive amounts of sulfuric acid in the atmosphere. The two scientists, completely unaware of each other's work, hit upon two different anomalies linked by a single date.
I was finding a cooling event at 75,000 years ago, and Greg, I later found out, was finding an increase in the chemistry of the ice cores 75,000 years ago. And we got together and realized that we had the same problem.
When you can look at something from different angles and see the same major result, you know you have found something that was huge, something that was a major force on the Earth's climate system.
Only a few natural phenomena could have created such a powerful force. One is an asteroid. Asteroid impacts blast debris into the atmosphere that blocks the sun's rays and cools the planet. But those impacts do not produce sulfuric acid. There is another possibility. Volcanic eruptions are known to pollute the atmosphere with sulfuric acid. But there's still a problem. Even history's biggest eruptions produced only a tiny fraction of the sulfuric acid Greg Zelinsky found. For an eruption to have cooled the climate and poisoned the atmosphere worldwide, it had to have been thousands of times more powerful than any in recorded history. Could such a volcano have ever existed? Without knowing it, another scientist is about to step into the mystery. His name is John Westgate. Westgate is a quaternary tephrochronologist. In plain English, a volcano detective. Westgate can identify a volcano anywhere in the world using just one critical piece of evidence: volcanic ash. Give Westgate some volcanic ash, and he'll track down the volcano that produced it.
We try to find out where the ash comes from, its parent volcano. And in that framework, it's exactly like a DNA signature.
Volcanic ash from every eruption is unique. It has a specific mixture of rock fragments and minerals that can point to its source. During an eruption, magma forces its way up through cracks to the surface of the Earth. If volcanic gases can escape from the magma easily, it produces a flow of lava. But if water and gases are trapped in the magma, it can explode with tremendous force, shattering solid rock and transforming magma into tiny particles of volcanic ash.
There are many factors that will affect the ultimate composition of a magma. The original source rocks from which these magmas are derived vary in composition. As magmas move through the Earth's crust, they might meet other magmas and mix together to form quite different material.
For decades, Westgate has successfully linked ash to specific volcanic eruptions across the world. But in 1990, Westgate ran into a problem.
I started to get boxes of volcanic ash from many different people, and these samples are coming from widely separated parts of the Earth's surface. And when I started to look at this material, look at the volcanic ash, I found that chemistry was very, very similar.
This similar chemical composition suggested to Westgate that all the ash came from a single volcanic eruption. But ash from a typical eruption rarely falls more than a few hundred miles. Yet these identical ash samples were collected from over 4,000 miles. If a single volcano were responsible for all this ash, its eruption must have been more powerful than any in recorded history. To determine if such a monster volcano ever existed, Westgate would need more clues. He would need to know the age of the ash, which he can find using a technique called fission track dating. He starts by sifting the ash, looking for one key ingredient: volcanic glass.
I sift this material to get the coarsest fraction of the volcanic ash, and then I would use magnetic separators to concentrate the glass from that coarsest component of the ash.
This volcanic glass is formed at the time of eruption from rapidly cooling magma. Etched inside the glass are microscopic-sized trails, or pits. These trails are caused by the decay of radioactive uranium-238, always present in magma. By counting the number of trails and knowing the rate at which uranium-238 decays, Westgate can calculate the age of the ash and when the volcano erupted. But when Westgate completed the process, what he found shocked him. All these samples, from locations thousands of miles apart, were the same age, 75,000 years old. The clues were lining up. Westgate's ash samples are the same age as Greg Zielinski's evidence of sulfuric acid in the atmosphere, and Mike Rampino's discovery of a catastrophic cooling of the oceans. These three scientists, working independently, are closing in on an unimaginable volcanic event. An eruption that could only be produced by a volcano larger than any known in history. Now, all Westgate has to do is find the volcano.
We started to search for volcanoes in other parts of the world to see if we could find the suitable candidate.
Westgate puts out the call to his colleagues to send in samples from all the volcanoes they're working on. It is the start of one of the biggest detective hunts in the history of volcanology. The first likely suspect that Westgate scrutinizes is the Laki volcano in Iceland, close to where Zielinski found evidence of sulfuric acid in Greenland's ice cores.
Well, Greg found this sulfur peak in the Greenland ice core, and Laki obviously would be a possible candidate for that, given the proximity of that volcano to the Greenland ice sheet.
When the Laki volcano erupted in 1783, it spewed over 200 square miles of lava. So deep, it would have buried the island of Manhattan more than halfway up the Empire State Building. It was one of the largest outpourings of lava in recorded history. The effects of Laki spread far beyond Iceland. Throughout Europe, volcanic gases killed trees and other vegetation and plunged the continent into one of the coldest winters ever recorded. Benjamin Franklin, who was then the U.S. ambassador in Paris, wrote about the sulfur-laden haze that hung over the city. Franklin was one of the first to link volcanic eruptions and climate. But the impact of Laki's volcanic gases was the worst in Iceland, killing 9,000 people, a quarter of its population. Marie Edmonds has investigated how this happened.
Laki was a devastating eruption which killed thousands of people, and this was mainly through famine, crop failure, caused by the emission of very large quantities of sulfur dioxide into the atmosphere.
Despite the vast quantity of sulfur dioxide Laki produced and its proximity to Zelinsky's ice cores, Westgate's tests show that the composition of the Laki ash does not match his mystery samples. But as he continues to receive new samples, he begins to see a pattern. The closer to Southeast Asia, the higher the number of samples. This region has over 70 known volcanoes. With one so violent, it stands out from all the rest. Pinatubo, in the Philippines, has erupted 7 times in the last 9,000 years, including one of the most violent eruptions of the 20th century.
3 reasons why we looked at Pinatubo. One is it was located in the right area. 2, it's capable of explosive volcanic eruptions. And 3, the overall composition of its volcanic ash is very similar.
Pinatubo's eruption in 1991 blew a vast 15-million-ton cloud of superheated ash and gas into the atmosphere.
When scientists saw the speed at which this huge sulfur dioxide cloud, this aerosol cloud, spread around the planet, they were amazed. I don't think anybody would have imagined that the effects could occur so quickly after a large eruption.
Hundreds of people lost their lives, and at least 50,000 were made homeless. Westgate immediately put ash from Pinatubo under the microscope. At first, it appears to be similar in composition to the mystery samples. It was rich in silica, typical in the ash of extremely powerful eruptions. But by the time Westgate concluded the analysis, his hopes were dashed.
When we started to look at the samples in detail, making those comparisons, we found that in detail they clearly are different. So we had to look elsewhere.
Days turn into months, months into years, as Westgate eliminates volcano after volcano. His colleagues continue to send new ash samples to the lab, but none are matching. It looks as if this is one volcano not even John Westgate can locate. Then, in the spring of 1994, Westgate arrived at work to find yet another sample. Its source, a tropical jungle in Southeast Asia, on the shores of Lake Toba. Lake Toba lies in the northern part of the Indonesian island of Sumatra. The lake is one of the largest natural features of the southern hemisphere, clearly visible from space.
What's unusual about Lake Toba is its dimensions are incredible. It's 100 kilometers long from that end up to that end over there. It's 30 kilometers wide from the upper rim behind us over to the other side.
Craig Chesner, a geologist from Eastern Illinois University, is investigating how the lake was formed.
What we're trying to do out here today with this depth finder is to get a profile of the lake bottom, because by getting a profile of the lake bottom, we can interpret the history of Lake Toba much better. We're starting to get a profile over here. You can see it dropping right off, 23 meters. And that cliff face, it just must keep on going straight down almost.
Most lakes drop off gradually from the shore, but Chesner finds that's not the case here at Lake Toba.
It's 175 meters deep already.
That's incredible for just a lake.
The incredibly steep slopes that drop off from the landscape up above. In some places, the rim is over 1 kilometer above lake level, sheer drops down to the lake, and then as you can see on this profile, it continues down beneath the lake with that sheer drop-off.
This steep line on the screen shows that Lake Toba is no ordinary lake. And its steep profile is not its only curious feature. As Chesner climbs high above the waterline, he finds something intriguing.
Wow, there's some really big pumices in this. I can see quartz crystals, I can see biotite, and there's a lot of ash in here.
Pumice and ash are telltale signs of a volcanic eruption.
This rock was definitely generated in a magma chamber, but look at the incredible extent of this. It extends all the way up to the top of the cliff face here. This represents a tremendous amount of magma, and the really strange thing is this is thousands of times greater than you find at typical volcanoes.
Everything Chesner sees in the landscape of Lake Toba points to a huge volcanic eruption. He sends an ash sample to John Westgate. Westgate puts this sample under the microscope, and things begin to fall into place.
Once we had looked at the samples from Toba, lo and behold, it was exactly the same.
Chesner's Lake Toba sample matches up perfectly to the mystery ash samples Westgate had received from multiple sites spanning thousands of miles across Asia. It has the same chemical composition, and it dates to 75,000 years old. Finally, after years of searching, Westgate has his match. Together with Zelinsky's ice cores, Rampino's ancient seashells, and Chesner's geological survey, the evidence points to an enormous eruption at Lake Toba 75,000 years ago. But if no known volcano comes close in scale today, how could such a powerful volcano have ever existed? The answer is a relatively recent discovery: a supervolcano. To qualify, a volcano must produce at least 240 cubic miles of magma in a single eruption. It takes the Mississippi River nearly 2 years to dump the same volume of water into the Gulf of Mexico. A supervolcano can put as much ash and rock into the air in just a few days. While over 1,000 normal volcanoes dot the Earth, none approach the scale of a supervolcano. Their eruptions dwarf even the greatest of the 20th century.
When you see the footage of Mount St. Helens, it looks like a really awesome eruption. Big, tall ash column. It looks like there's tremendous power there. But that eruption only erupted 1 cubic kilometer of magma. So, as you can see, that's very much smaller than any supervolcano eruption.
An eruption thousands of times more powerful than Mount St. Helens has never been witnessed in modern times.
It's almost impossible to imagine the scale of an eruption such as Toba.
Toba is not the only site of a supervolcanic eruption. By studying ash samples and taking geological measurements, volcanologists are also discovering evidence of supervolcanoes in Italy, New Zealand, Japan, and the United States.
Supervolcanoes are not as rare as we might think. They're all over the place, but they have very, very long times between eruptions, so that we don't see them go off in historic times.
In the last 2 million years, we know of 4 active supervolcanoes: Lake Toba, Long Valley in eastern California, Taupo in New Zealand, and Yellowstone National Park, which sits on top of a supervolcano. Based on ash sample analysis, Yellowstone's supervolcano has erupted 3 times. Its oldest, 2.1 million years ago, was possibly Earth's most massive volcanic event, spreading ash throughout North America. Just like smaller volcanoes, supervolcanoes start with a column of magma rising from deep within the Earth. But while smaller volcanoes explode to the surface, where their magma hardens into the familiar cone shape, supervolcanoes are chiefly known for storing massive amounts of magma in vast subterranean chambers. Toba's held nearly 1,800 cubic miles of sweltering magma, enough to fill 200 Grand Canyons.
We think that it might have taken 1 million years to accumulate all the magma that was beneath Toba.
As the magma and volcanic gases accumulated, pressure built up in the magma chamber, putting the Earth's crust above under incredible stress.
Magma would have been accumulating beneath this area, doming up the entire terrain.
It certainly would have involved new cracks opening up in the ground.
After millions of years of accumulated pressure, the magma finally erupted, draining the underground reservoir.
The roof of the magma chamber, though, began to collapse and sink into the magma chamber. This forced the silica-rich magma out along the perimeter of this collapsing roof block.
Once the eruption started, all hell would have broken loose.
This magma erupted explosively towards the surface, generating enormous ash clouds and generated pyroclastic flows,
which are very destructive and hot avalanches of gas, ash, and rock. And of course, they destroy everything in their path.
The mayhem would have continued for days.
Very high eruption columns. These eruption columns would have reached tens of miles into the atmosphere.
The eruption plumes sent billions of tons of ash around the globe, some of which eventually ended up in John Westgate's lab 75,000 years later.
That, for me, was the eureka moment, when we had brought all this chemistry together, combined it with the dating, and it all gave this coherent story of one massive eruption 75,000 years ago from Toba.
But still one mystery remains. In this tropical landscape of jungles and lake, where is the supervolcano today? It's hiding in plain sight. Lake Toba is the massive scar the volcano left behind. And the lake water is thousands of years of rain.
This eruption created this crater, this enormous crater that we're sitting in. This island here actually slid down off the walls of the crater during the eruption. Now we know that Lake Toba is the site of one of the largest volcanic eruptions ever to occur on Earth.
The discovery of the Toba supervolcano raises another question. How did the eruption impact life on Earth? When Toba erupted 75,000 years ago, the Earth was abundant with animal life, but only sparsely populated by our human ancestors. Recent fossil evidence suggests that Homo sapiens had already started the migration from Africa, reaching Asia 80,000 years ago, well before the Toba eruption. The cataclysm would have annihilated virtually all life, human, animal, and plant, within a wide radius. Death from breathing in volcanic ash would have been excruciating.
Well, if you're close enough to the volcanic eruption, and in a super eruption that can mean thousands of miles away, if you breathe in the ash in an unprotected way, you're breathing in tiny little glass needles. And they get into your lungs. They cause the blood vessels in your lungs to pop. There's moisture in your lungs. The ash combines with the moisture to make a kind of a cement. You basically choke to death.
Ultimately, the most catastrophic effects of the volcanic ash and gases may have been on the planet's climate. The key culprit would have been sulfur.
Sulfur can reach very high altitudes. In the atmosphere, it combines with water to make sulfuric acid, which is a liquid, which forms tiny little droplets. And it's that mist of drops of sulfuric acid that present the veil that cuts out the sunlight, that scatters the sunlight back to space, that keeps the sunlight from getting to the surface of the planet, to warm the surface of the planet.
This sulfuric acid cloud blanketed the eruption site, then quickly spread over large areas of the globe. Particles in the cloud scattered sunlight, causing the sky to appear blindingly bright, but blocking the warming rays of the sun. Since the climate was already in a cooling phase, it's possible that Toba jump-started the Earth into a prolonged freeze.
But based on our present information, Toba had a major role, in causing a 1,000-year climate cooling and created a mini ice age that lasted at least 1,000 years, perhaps longer.
Rampino has shown that the biggest historic eruptions cooled the planet over many months or even years, a phenomenon he calls volcanic winter. So how much more would an ancient super eruption cool the planet? To find out, NASA climatologist Drew Shindell created a computer model based on scaled-up data from smaller historical eruptions.
In our simulations, the planet definitely cools in response to this super eruption. The cooling is larger than you'd expect just from having the eruption itself.
This exponential cooling has a surprising cause: snow.
We think Toba could have pushed the planet towards an ice age because the model was able to increase the area covered by snow. So that makes the planet brighter, more reflection, and then even after the volcanic material has fallen out from the atmosphere, the brighter surface can allow the cooling to continue.
The reflective surface literally had a snowballing effect. The more snow, the more the reflection, the more the temperature dropped, causing even more snow and ice. Glaciers advanced, and the temperature of the oceans fell.
Ocean surface temperatures started to cool. And by doing that, you're looking at a major part of our entire climate system, considering that the ocean covers 75% of the Earth's surface. This has a major impact on our climate.
The tiny ocean creatures called foraminifera are proof of a global disaster 75,000 years ago. In Greenland, over the millennia, snow compacted into ice more than a mile deep to form the Greenland ice sheet. The 75,000-year-old snow sees the light of day for a second time when drilled up by Zelinsky and his team. Vegetation withered and died. The food chain was disrupted, and animals and humans starved to death. The Earth continued to freeze until a new climatic cycle swung it out of its mini ice age into a warmer phase. The supervolcano that caused all this is ancient history. But could it happen again? Today, Lake Toba is the picture of serenity. Craig Chesner continues his study of the lake and its supervolcanic origins. But now his investigation is taking on a new urgency. For below the calm waters of Lake Toba lies a ticking time bomb.
We're standing here on the western shore of Lake Toba in this area of white rock, and the reason it's this color is because there are corrosive gases permeating through the rock, hot fluids coming out of the rock making this stream here, and they're incredibly hot. I can barely keep my hand in there. It's about 80 degrees Celsius. This tells us that magma is not too far beneath us at this particular location. That definitely demonstrates that Toba is an active volcanic system. There's magma beneath the surface, and a good chance that there will be volcanic activity in the future.
Toba appears to be on a roughly 400,000-year cycle, so an eruption is not likely in our lifetime. But the activity in its magma chamber and those of other known supervolcanoes indicate the threat is real. The Yellowstone magma chamber is the largest known on Earth, encompassing half of the 3,500 square mile park above it, and extending nearly 5 miles deep. It too appears to be filling.
At Yellowstone, they're seeing a bulging of the Earth's surface, which they've been measuring for years.
Yellowstone erupts about every 600,000 years. So there's a cycle of filling the magma chamber and the magma sitting there becoming more silicic, more ripe for an eruption, and then there's an explosion.
With its last eruption 640,000 years ago, and Yellowstone on a 600,000-year cycle, another eruption may not be that far off. A future eruption could devastate most of the continental U.S. and blanket ash all the way to the Atlantic coast. Now, with 6.5 billion people on the planet, the next supervolcanic eruption will have a vast impact on our modern world.
Well, a supervolcanic eruption would affect all aspects of modern life, of modern civilization, food resources, climate, water availability. The water would become polluted by the ash. The crops would fail. The livestock would die. Machinery would get clogged by the ash, so that automobile filters would clog. You can't drive. The jet engines on commercial airliners would clog up. And so worldwide air traffic would come to a standstill.
Supervolcanoes are among the most destructive natural disasters on Earth. Yet only now are the secrets of these sleeping giants being revealed.
Volcanology is still a really young science, and there's so much that we still don't know. And only really by coming out here to these volcanoes can we hope to predict or forecast volcanic eruptions in the future. Especially very large ones, which could have a very large impact on our way of life.
Whether the next supervolcanic eruption will be at Yellowstone, Toba, or somewhere else is difficult to forecast. But what is certain is that it's just a matter of time before one of these megavolcanoes awakes.